Okay, let's start our presentation. Our presentation title is Homomorphic Commitment Scheme with Low Upper Locality. Authors are Hideaki Miyaji, Atsuko Miyaji, and Yuta Wang, and speaker is Hideaki Miyaji. We do our presentation as this online outline. So let's start our presentation. We start from introduction. So what is commitment scheme? So commitment scheme is the protocol which is sender and receiver. And there is two phases, which is commitment phase and decommitment phase. In commitment phase, the sender chooses the message value and convert the message value to encryption value, which is C. And they send the commitment value to receiver. So this is commitment phase. In decommitment phase, the sender sends the message value and the key of commitment value. So they only, in here, they send M. And receiver verify com M, and which is equal to C or not. So these steps are called decommitment phase, and commitment phase and decommitment phase we called commitment scheme. In commitment scheme, have to prove that sender is secure and receiver is secure, which is called hiding and binding property. So commitment scheme is a secure communication between sender and receiver. However, let's think if the number of sender increase. So if the number of sender increase, then that means that the commitment value which receiver receive is going to be increased. So that means receiver have to get the many value of commitment value. That is so problem. So we have to reduce the data space of receiver. How we achieve this? Homomorphic commitment scheme. So if homomorphic commitment scheme can be done, then we can overcome this problem. Since that we can enable to aggregate the encryption value, which is commitment value. For example, we can achieve it in transaction in Bitcoin. So homomorphic commitment scheme is suitable for protocols who has large number of sender. So next, we talk about upper locality. So what is upper locality? So definition of upper locality is the function f has upper locality d if each output depends on at most d inputs. Let's see for example. So this function f has 7 input bits and 3 output bits. So y1 and y2, y3, y1 depends on 3 input bits, and y2 depends on 5 input bits, and y3 depends on 3 input bits. So in this function, its upper locality is 5, since the maximum of the number of inputs in y1 to y3 is 5. So the upper locality in this function is 5. And also, there are also the feature of upper locality is if the upper locality is constant, then paradigm complexity is constant. And next, we think that we are said that if the quantum computer has begun, then they can break many security primitives that exist now. So we need to construct a protocol for quantum computer, which is lattice-based. So we have 3 features here. That is, upper locality is able to incorporate into lattice-based. And hash function is able to construct based on upper locality. And one more thing, homomorphic commitment scheme can be constructed based on hash function. So we combine these 3 features, and we can say that homomorphic commitment scheme based on lattice with constant upper locality, it can be done. How can we done? Next. So to apply homomorphic to previous research, we talk about previous research, which is defined by using upper locality. These 2 previous research is both low upper locality. However, they both had not homomorphic features. So why they have no feature of homomorphic? That is that they use the assumption, bSVP assumption, which does not satisfy homomorphic features. So what is bSVP assumption? bSVP assumption is constructed by M times EX, which M is a matrix and EX is a restriction relative Hamming weight. And this restriction relative Hamming weight have to be used since that they have the bSVP assumption have to be constructed by the restricted relative having weight. And this expand function is the reason that the previous research does not satisfy the homomorphic feature. So if the expand function satisfies the homomorphic feature, then we can construct homomorphic commitment scheme. So these are our main propose. So we propose a homomorphic commitment scheme with upper locality 3, which is constant upper locality, and based on M delta bSVP assumption, which is lattice space, is our main propose. And to propose these main results, we also propose detailed propose. That is, we construct homomorphic expand function. And we prove the homomorphic feature of a commitment scheme. And we also estimate the parameter of a security assumption, which is M delta base assumption. So next, we talk about our preliminaries. So before we talk about preliminaries, we talk about abstract of preliminaries. So they have expand function. We construct expand function since we want to construct bSVP assumption. And we construct collision resistance hash function based on bSVP assumption. And in this collision resistance hash function, there is no restriction of upper locality. So to have constant upper locality, we apply PRE to this collision resistance hash function, and we construct collision resistance hash function with upper locality 3. So we apply this hash function to commitment scheme. So we talk about this feature in preliminaries. So this feature, collision resistance and M delta bSVP assumption and expand function, we talk here. So what is collision resistance? Adversary. So probability that adversary output X and X prime, which satisfied Fx equal to Fx prime, is lower than negligible, then the function satisfies collision resistance. Next, M delta bSVP assumption. So adversary given the matrix M and output X, which satisfies M times X equals 0. The probability that adversary output X is lower than the negligible is called M delta bSVP assumption holds. And here, X have restrained that relative having weight of X should be smaller than delta. Next is expand function. So expand function is given k bit of X and expand bit of n bits, which satisfies the relative having weight of delta over 2 is expand function. So next is the perfect randomized encoding, PRE. So we use PRE to construct the constant upper locality. So how we construct is given F as n bit to n bit function. And F hat is a PRE of F if there exists the efficient decoding algorithm of C and randomized simulator of S and satisfies these 4 notation features. So because of the time restriction, we omit the explanation here, and please look our paper. So why? So feature of PRE, if the function F has collision resistance, then the function F hat has also collision resistance. So we can construct F hat with constant upper locality with collision resistance. Next, we talk about previous research. We talk about 2 previous research, which is hash function and PRE function. So previous research using hash function using expand function. So they input k bit of X and matrix M and relative having weight of delta. They first compute expand function and expand the k bit to n bit. And next, if the relative having weight of this one is smaller than delta over 2, then they compute M times expand X and output Y. Then this Y is a return of this hash function. And this hash function's illustration is written here. So we denote 3 symbols in here. So beta, we call delta over 2, and B as expansion rate, and alpha as a compression rate. And the collision resistance of hash function has to satisfy these 2 conditions. The relative having weight of expand X is smaller than beta, and the delta is smaller than alpha over 2. So next is PRE function of previous research. So let ft as a function. F is a function from n bit to 1 bit. And we select R and R prime, and we construct f hat, which is PRE of f as the output of this one. So there is T1 to T blah blah, and we set upper locality of Ti as D. So there's upper locality of Ti is D. So that means that each output bit depends on at most D plus 1 input bits. So that means that this upper locality does not depend on input number. Because that this upper locality is constant upper locality. Okay, so finally, we will propose our results. So before we talk about our results, we will talk about our abstract of our results. So we propose the expand function of a homomorphic named MATX. So we propose MATX and apply bSVP assumption by using MATX. And we construct coordinate resistant hash function named HML of bSVP assumption. So this coordinate resistant hash function has homomorphic. And we apply PRE to CRH, and we construct the PRE CRH, which is CRH with upper locality 3 with homomorphic. So these are the hash function. So we apply this hash function to commitment scheme and achieve that commitment scheme with upper locality 3 and homomorphic. Okay, now let's start our proposal. So we first propose our function MATX. The condition of expand function that is need that injection and the relative having weight of x is 0 to 1 over 4, and delta is smaller than alpha over 2. So our matrix is input k-bit vector of x and random matrix L. This random matrix L, we can select uniformly random matrix L, which satisfies rank is k. So any matrix of L is alright if satisfies rank L equals k. And we compute L times x, and we output this L times x as an output of matrix. And we prove that our matrix satisfies these three features in theorem 1. That is, matrix L is injection, and the relative having weight of LX is more than 0 to 1 over 4, and delta is more than alpha over 2. So please look at the more detailed information of our paper. So next is our proposal hash function HML. So this hash function HML is similar to the previous research of hash function. So we have an input of x, k-bit of x, and matrix M and L, and delta. So we first compute L times x. So if the relative having weight of Lx is smaller than delta over 2, then we compute y as M times L times x, and we output y as output of this hash function HMLX. So before we talk that collision resistance of hash function, there need that two conditions. That is, delta relative having weight over L times x is smaller than the delta over 2, and delta is smaller than alpha over 2. And we proved that our hash function HML satisfies these two conditions. So this hash function HML satisfies the conditions of collision resistance, and HML satisfies collision resistance. So next, we propose our PRE hash function HML xt. So we first input of x, k bit of x, and matrix M, and random number T, and matrix L. So we first compute M times L, and we separate. So we have matrix M times L as C11 to CMK part. And we compute C11 times matrix 1x to CMK times matrix k, which is equal to M times L times matrix. So we compute y hat from this computation of value and random number T by using same way as the previous research. And the output of y hat is written as this one. In here, output of y can be classified as 3 patterns of y hat yij, y hat ij, and y hat I xt, and y hat I 1 plus k. These 3 output of output locality is 3 and 2 and 1 respectively. So that means that output locality of y hat is 3, since that the number output locality is a maximum of output locality. So our hash function, PRE hash function y hat, is output locality 3. So next, we propose our commitment scheme, com. So this commitment scheme is based on PRE hash function, which we proposed the previous slides. So sender choose message value A and random number R and random T, and compute y hat as the same as PRE hash function, and send the commitment scheme com as a commitment string to the receiver. This is the end of commitment phase. In decommitment phase, we send decommitment string, which is key of commitment scheme, A and R and T. And the receiver will compute commitment com of A, R, and T, and is equal to y hat or not. This is a commitment scheme based on our PRE hash function. Next is we have to prove that our commitment scheme satisfies homomorphic or not. So our commitment scheme, commitment scheme A, R, T is additive homomorphic. So how to prove this? We have to prove commitment scheme is additive homomorphic. That means that com A, R, T and com A, R, M prime, R prime, T prime is equal to this equation. And our PRE hash function has three types. That is 1 and 2 and 3. And if the below equation, so if the three equation satisfies homomorphic, then we can prove that our commitment scheme has homomorphic. And we prove that 1 to 3 equation satisfies homomorphic. So we can say our commitment scheme com is additive homomorphic. So this is our proposal of homomorphic commitment scheme. So we also did a parameter suggestion. We evaluate a secure parameter on M delta bSVP assumption by using 2060 estimated. So table 1 shows a secure parameter on using commitment scheme com. So this is conclusion. So we propose a homomorphic commitment scheme with output locality 3. And we achieve the following results. We construct a homomorphic expand function. And we prove the homomorphic feature in com. We estimate the parameter m and n and delta as follows, that if m and n and delta is this value, then it is secure under AES 128. And if m and n and delta are equal to this value, then it is secure under AES 192. And if m and delta is this value, then it is secure under AES 256. So this is our references. Thank you for listening.